Hello, this is the next video in the series on the bracket notation for proofs. And the purpose of this video is to discuss a bit how does one structure individual lines of a proof. So recall that a proof laid out in bracket notation consists of lines, and each line will be a mathematical statement, which can be actually written out in English language as well. But the most symbolic form of a mathematical statement, where we only use symbols, is what we're going to discuss in this video: how to structure those symbolic forms of mathematical statements. Because they are useful, first of all, because they make things shorter, but also because they help us navigate through the proof, and later we will see that they help us to confirm when something is a valid conclusion when a line is a valid conclusion of the previous lines or not. And they also help us structure the entire bracketed proof. So they've got lots of meaningful uses. So the purpose of the symbolic notation is very much to help us figure out basically mathematical proofs better, and to make things more precise also, because the English statements can get very imprecise. As you know, mathematics requires a certain level of precision that can't really be accessed using ordinary language. And so basically we're going to look in this video how the logical symbols can be used to express ideas, mathematical ideas, in a purely symbolic and hence very precise form. And so these lines that we're going to be writing in this video, they are the kind of lines that you will see in each line of a proof structured in the bracket notation. First, let us introduce the symbols that we have available for expressing the mathematical phenomena. So we will not touch on all the available symbols in this video. We will look at some of the most basic ones. Here we have a symbol for AND, and the way it's used is that some mathematical term, something that represents a mathematical object, made a mistake there, not a term, but a mathematical statement. So I'm going to use Greek letters for representing mathematical statements. So a logical statement that has a meaning that could be true or could be false, even if we can't figure out which of the two, can be combined with another such statement using this symbol. And when we combine them like that, the combined statement obtains its own logical meaning. In the case of the symbol, the meaning is that alpha is true and beta is true at the same time, so they're both true. The meaning of mathematical statements, usually when it comes down to validating proofs, the meaning comes down to whether something is true or false. So alpha is a statement that could have this truth or false meaning, and same for beta. And the new statement we form from them, alpha and beta, the truth meaning of this is that alpha must be true and beta must be true. So in other words, they both must be true. Okay, so I'm going to be writing the usage of a symbol on the right hand side and the symbol itself on the left hand side. So you see this symbol called conjunction takes input two mathematical statements. So let me draw this vertical line to distinguish between the symbols and their usage. So this thing is called conjunction, as I already said. Maybe I will actually not write this down here. Maybe I will make a separate space for that. Let's write it on the left side here. Okay, so I'm about to type this in. My computer is slow. There we go. It's working now. Adjusting this font size. Conjunction. Maybe I want to make this just a bit bigger. There we are. So this symbol is called conjunction. It means and. It reads and in its usage. And perhaps I should also display how one reads it in this column here. Or maybe rather say how one reads the entire thing once the symbol has been used. So this would read alpha and beta. Okay. So next we have something that looks the previous thing upside down. This will represent a mathematical OR. So again, it works in a similar way. There are two input statements, and the entire thing will read alpha or beta. And the logical meaning of this, the truth meaning of this, is that alpha is true or beta is true, without excluding the possibility that both of them are true. So in fact, it's alpha true or beta true or both of them true. Okay, so that symbol is called disjunction. And then we have another symbol, this one, which is called negation. And the purpose of this symbol is to oppose a given statement. And so this one takes only one input. The input of this is just one statement, let's say alpha, and we will read this as not alpha. And the logical meaning of this is that alpha is not true. So if alpha was true, then this thing would be saying that alpha is false. If alpha is false, what did I just say? I said if alpha was true, then this thing would be false, because it is not true that alpha is not true when alpha is true, right? On the other hand, when alpha is false, this will be saying that it is not true that alpha is true, which is true. So when alpha is false, not alpha will be true, right? There are also these truth tables, right, that kind of describe this more accurately, the logical meaning of these constructs here. And so let me draw the truth tables as well. So for and, the truth table goes like this. So the left, the rows are going to represent alpha truth values, and the columns are going to represent beta truth values. And so when is alpha and beta true? When both of them are true, certainly it's that the case. And that's the only case, actually, right? As soon as one of them is false, we can't say anymore that both of them are true. So then all the other values are false. And for disjunction, let's see what will the truth values there be. So again, rows represent truth value for alpha and columns for beta. And so alpha or beta will be true in all the cases except one case when both of them are false. So alpha, if alpha is true and beta is true, then alpha or beta will be true. When one of them is false, it will still be true. And the only case when this thing will be false is when both of them are false. And you will see how this is kind of dual to the other one. There, the only case when that thing was true was when both of them were true. So that was the only case. The rest were false. And here we have the other way around. There is one false and the rest are true. And then we can also draw a truth table for negation. So this matrix doesn't quite work when there aren't two inputs. So there's also another way of displaying such things. I'm going to draw alpha here, write alpha then, and here I'm going to write not alpha. And so I can put two inputs there, true TF. And so when alpha is true, not alpha will be false. When alpha is false, not alpha will be true. Now, while we have these truth tables, we actually don't really want to use them too much in structuring proofs. This is more for our understanding of the logical intuitive meaning, the intuition of the logical meaning, basically. Because in a mathematical proof, we want to be able to make conclusions there, not based on these truth tables, but rather based on logical rules called deduction rules that will tell us when can we write down the next line as a conclusion, like a line like this, once we are given the previous lines. And then depending on these logical rules, we will actually be able to derive some of these truth tables from those, but some truth tables require certain rules that we might not want to use already from the start. So these truth tables are not there for us for them to be used inside the proofs. They're rather there for us to have an intuition for interpreting the meaning of these constructs. Okay, then we've got also the symbol called implication. And that one again has two inputs, alpha and beta. And the way we can read this is alpha implies beta. And the logical meaning of this is that if alpha is true, then beta is true. But this doesn't give full justice to the symbol, because in ordinary language, when we say if then, we sometimes have something slightly different in mind than purely logical dependence in terms of truth values. So let's clarify this with the truth table. So depending on the truth of alpha or beta, when will alpha implies beta be true or false? So if alpha is true, then beta must be true. So if alpha is true and beta is both of them true, then alpha implies beta is fine, it's true. Because we're saying if alpha is true, then beta must be true, and that holds when both of them are true, right? We haven't violated the fact that if alpha was true, then beta is true under the scenario when both of them are actually true. When alpha is true but beta is false, then there is a violation, right? We said if alpha was true, beta must have been true, and if we're given that alpha is true, then beta must be true, and now if beta is false, that violates that. So when alpha is true and beta is false, then alpha implies beta is going to be false. Remember that the rows represent truth values for alpha and the columns for truth values of beta. So with this truth value of alpha, T standing for true, and this truth value of beta, F for false, we get that alpha implies beta has this true value. Okay, now what about the scenario when alpha is false and beta is true? When alpha is false, we already are not violating anything, because the statement tells us if alpha was true, then something should have happened. But if alpha is false, then there's no way that will be violated, because alpha is false, so it will never be true. And this is where the confusion might come in, because now we say alpha is false, it can never be true, but what if it becomes true at some point, right? And then we actually don't care about that. So if it becomes true at a different point, then we will reevaluate the truth value of this, right? So the current moment when alpha is false, the statement that if alpha was true, then beta, whatever, doesn't matter what, will not be violated, simply because alpha is not true. So this statement does not give us any responsibility for anything to work out, because we're only saying that we will get implication for beta under the condition that alpha was true. And so if alpha isn't true, then nothing has been violated. And when nothing has been violated, we think of that as the statement being true. So irrespective of what beta value is, whether it's true or false, alpha implies beta is going to be true when alpha is false. So these are the logical symbols. There is also another one called equivalence. Which also takes two inputs, and we say that alpha is equivalent to beta. Another way we encounter this construct in mathematical proofs is when we say if and only if. So if we say something if and only if some other thing, that is the bidirection and implication. We're saying if alpha then beta, and if beta then alpha. And what I just said now basically defines this. So we can actually define this as an abbreviation for, so we can say this thing is equal to, for the statement alpha implies beta and beta implies alpha. And so let's see what the truth table for this will be. I'm actually going to show you how we can design this truth table, how we can come up with it by already making use of the previous truth tables and this definition for equivalence. So I'm going to now not use this matrix notation, rather the notation that was used for the negation. So I'm going to write alpha and beta here, and what I will do below them is list all possible combinations. So alpha true, beta true, alpha true, beta false, alpha false, beta true, alpha false, beta false. And then I will consider each of these. So alpha implies beta, right? Make a column for that, which will be derived from the column from the truth table for implication, and then a separate one for beta implies alpha. And then at the end, finally, what I'm going to do here is to have a column for alpha implying beta and beta implying alpha. And so, whereas these columns will be determined by this truth table, then this last column will be determined by making use of these truth values we will get in these columns and making use of this truth table. So let's look at the first line. Alpha true, beta true. What will happen if alpha implies beta? Well, we can either apply our understanding of this implication or just read it out from the truth table for implication. So when we see that alpha is true and beta is true, then alpha implies beta is also true. So we write T here. And remember, for implication, the only time the thing is false when alpha is true and beta is false. So let's look at for that entry. So this is alpha is true and beta is false. That's the only time it's false. The rest of the times it's true. So we can just complete it like that. Now for beta implies alpha, the only times it's false is when beta is, so now the roles have swapped around, right? So now I have to think these columns being swapped around. Now I'll be reading out the truth value of beta here from the rows, and the columns will represent alpha. So beta being true and alpha being false, that's the only time when this will be false. So let's see, when is beta true and alpha false? It's this entry here. So that's the only time it's false. The rest are true. Okay, and now I've got here, you can think of this as two statements, let's say gamma and delta. And now you've got your gamma and delta. And so we can read out what will go here. We can read it out from this truth table. True and true gives true. You see, true and true here gives true. False and true gives false. True and false gives false. True and true gives true. We now see what the truth table of this thing will be by going back to the original first columns and kind of highlighting this perhaps. So now what we're interested in is to read this information here, which will tell us the truth values of the equivalence based on the truth values of alpha and beta. And you see that the only times that the equivalence is true is when alpha and beta are both true, and also when alpha and beta are both false. And that makes sense because equivalence means that they should be logically equivalent. That means that they should have the same truth values, right? So you can't have alpha equivalent to beta when alpha is true and beta is false. That doesn't make sense. And so we come to a conclusion through this computation, which agrees kind of with our intuitive sense of equivalence. So we can be confident that this is the right way of defining equivalence by making use of conjunction and implication. In fact, this will be useful in structuring proofs because very often we would want to break this up into this its decomposition and then prove the statement by proving. So how do we usually prove something with an n, right? We would prove this and that separately, but that's still to come in a later video. Okay, so what we've discussed here are all the logical symbols that don't make use of variables, that only are used to combine existing statements, but there is no, as you see, there are no variables representing specific objects about which the statements are. So there are two other symbols for that purpose, for the purpose of introducing variables into the story, and we're now going to discuss those. Okay, so let's have a look at that. So now we will expand our table here a little bit. So the next one we will have here is called Universal Quantifier. And the symbol for it is this, upside down A. And here is how we use it. We will write upside down A, and then a variable, and then some mathematical statement, which might have this variable present inside it. And to indicate that, we will put x in brackets here. So that's how the universal quantifier is used. Now, how do we read this thing? One of the ways of reading this is to say, for every x, alpha x. And the logical meaning of this is then tied closely to how we read this. So alpha was a mathematical statement that involved an object x, and the object x wasn't specified in advance. So it's the x is just a name for representing general objects, but at each particular point, when we want to give a logical interpretation of this, we have to think of x as something specific, but we are not allowed to do that yet before we combine that ingredient with this ingredient. So alpha is just some statement about some object x. We don't know anything about this object at this point except whatever alpha states about that object. And what we're saying here with this whole thing, we're saying that that statement alpha must be true irrespective of what the object x is. So it must be true for all possible values of x. That's the logical meaning of for every x, alpha of x. Another way to read this also is to say for all x, and this all, the a from all kind of ties with the upside down a we've got here. So let me rather use that. So we have a logical symbol for expressing that some statement is universally true irrespective of what value x obtains, that this must be true. Like, for example, just to have one example, we could have alpha x saying that x can talk, and if our variables represent human beings, then we could make a claim that every human being can talk by writing for every x, alpha x. We touched on right now on a subtle phenomenon about the meaning of the scope of variables. So in a mathematical language, before we start writing things symbolically, we have to have an agreement as to what types of objects do the variables represent, what are they allowed to represent and what not. So that when we say for every x, then we will automatically be thinking of all possible values of x among those things that the variables are allowed to represent. So in this case, we wouldn't be interpreting this as animals can also talk, because we said that the variables represent just the human beings. The other logical symbol, okay, so one more thing I want to say about this is that we have nothing like a truth table for something like this, because the truth value of alpha x now becomes dependent on individual x, and there could be lots of different x's which could go into this, like there are lots of different human beings, right? And so there is not really a meaningful way of representing the logical truth meaning of this as a truth table, like we had it in the case of the other symbols. But remember that even in the case of those symbols, these truth tables will eventually fall away. We just displayed them for our own understanding of the logical meaning, but in the proofs, we're not going to make use of the truth tables. We will rather derive them by using deduction rules, as I mentioned earlier. So the rules which allow us to move from one line to the next line as a conclusion. And there will be also deduction rules for the universal quantifier. So this is where all the symbols will then come together under a uniform set of rules. And also the same applies to existential quantifier, which is our next symbol. The existential quantifier is written like this, and it can be used in this way. There exists x alpha x, and once again alpha is some statement about a general object x, and the way we read this is, as I said I think just now, there exists x such that alpha x, so that's how we read this, and then the meaning is also tied to this. So once again, if variables represent human beings, alpha could be saying x speaks French, and now we're saying, with this whole entire statement, we're saying that exists a human being that speaks French, which of course is true. However, if we go back to the universal quantifier, then it will not be true anymore, because then we will be claiming there that every human being speaks French, which clearly isn't true. But there does exist a human being that speaks French, and that's what this second thing represents, the one with the existential quantifier. So the term quantifier here appears to kind of quantify, to kind of give quantity to the amount of x values for which the statement should be true. And we have kind of two different extremes. One is when the statement is true for all x values, so when the quantity is the full quantity of all possible values of x, and the other is when the quantity has at least one thing in it. And it could still be the case that for every x alpha is true, but that's not what we're saying with this. We're saying that it's at least one. So although this seems to be kind of weaker statement than this, actually this one has one aspect that is stronger than this one. Namely, with this one, when we say that for every x alpha x is true, yes, we do know that if we have an x, then alpha x will be true for that x. But with this statement, we don't know that such an x exists or not, okay? And this is what this tells us, that such x does exist. So imagine, for example, I told you that x represents all Martians, okay? And consider a scenario where Martians do not exist. Then, if Martians do not exist and x represents all Martians, I mean x can represent any Martian, then the statement for all x alpha x, no matter what I put here, we can deem that to be true by the principle that, by the implication truth table, that the false premise can imply anything. So the assumption x is Martian, which can never be true because there is no Martian, can lead us to any conclusion. And so whatever we put as alpha x, for instance, we can say Martians speak French. So for every x, x speaks French. Now when the variable represents Martians, this is true simply because there is no Martian. On the other hand, this statement will not be true, because this will be claiming that there actually exists a Martian that can speak French. And never mind the French part, we know Martian does not exist. I mean, if it doesn't, right? And so already the existence part of that construct will be false. Whereas here, we're not claiming the existence. We're just saying that if it existed, whatever it was, alpha would have been true for that. But here, we're actually claiming the existence of at least one such object, and in addition, claiming that that object, or maybe another one, but at least one of those objects satisfies the statement alpha x. Okay, so this video is becoming longer than I originally anticipated. What we've done so far was to give kind of lay out the words, the basic words we're going to use in building the statements that constitute sentences, lines in the bracket proof notation. And so this is our basic vocabulary, the symbols we've introduced here. There is also another one that will be very commonly used, which is no longer kind of seen as a logical symbol per se. So the symbol of equality. So let's write this out as well. So the reason why I say it's no longer a logical symbol is because the input things for the equality symbol, I mean, we're all quite familiar with the equality symbol, right? So the things we will input here will be, unlike in the previous cases when the input was always, well, already here with the quantifiers, we already had a mixed scenario, right? There were two inputs. One was a variable, and the other was a statement. And here with non-logical symbols, the input is always a variable or another object that could be represented by a combination of variables. We'll talk a bit more about that later. So the way this is used is x equals y, where x and y are no longer statements, unless specifically we talk in this language about statements. And then, like for this equality here, for instance, we use this equality in a language where our variables now were Greek letters, actually, and we were talking about statements that are represented by those Greek letters. But we still want to keep distinction of the statements and the actual objects in another scenario where we don't explicitly discuss logic. And so the non-Greek letter variables, they will represent objects of discourse. And the way we read this is x equals y. And the logical meaning of this is that whatever the object is represented by x and whatever is represented by y, those two things must be actually the same object. So x and y are representing the same object. That's the meaning of x equals y. Now, in addition to these, so these are the standard symbols used in each mathematical exposition. But in addition to these, depending on what we want to talk about in our given mathematical language, we might want to introduce further symbols. So one actually can do that. One can introduce one's own symbols for as being part of the mathematical language. And this is how it becomes possible to express everything in the mathematical language, by adding these symbols. For example, we could add a symbol for love. So, of course, this symbol now will have very specific meaning in a very specific scenario, in the scenario where we talk about human beings and we want to study their relationships, perhaps. The usage of this will be that x loves y. So with these specific symbols, we will always have variables as inputs. And then this reads x loves y, but this is basically our own definition, right? So we can add such definitions as much as we like. So x loves y is how we read this. And now we can talk about what this means intuitively, just like we've been talking about what these other things mean intuitively, right? Then eventually we can transform this intuition into axioms that will enable us to do some actual mathematical proofs based on this love relationship, right? So we have a symbol for love. We can add anything we want here. We can add, so what would be another example of something we could add here? Let's add something like t. And let's say tx to mean x is tall. Right? There we go. This is a symbol for expressing that x is tall. Let's say we are talking about human beings here in this case as well. Then other symbols we would want to add would be, for instance, if we're doing arithmetic, we want to have a symbol for addition. and then we read this as x plus y. But now there is a subtle difference between those kinds of symbols we've been adding there and this kind. And the difference is that in the previous case, the thing we were writing down in the usage of the symbol was always a statement that could be either true or false. But here, this is not a statement anymore. This is an object. It's an object we create out of x and y, right? And such a fragment of mathematical language is called a term. This could actually be an input, for instance, in the place of x here, because x represents an object, and so we could have had x plus y equals y, right? And so we get that by replacing that variable x there with the term. So addition is a symbol that allows us to create terms. In other words, expressions that do not represent statements anymore, but they represent actual objects made out of other objects. We also have in arithmetic not just symbols for representing further objects, but also for expressing some relationships, like the love relationship, but now not with the same meaning, of course. So, for example, another relation we have in arithmetic would be the less or equal relation, right? Usually we call this inequality. This is its usage, and we would say x is less or equal to y. And then we could go on with this, right? Another example of a term would be a symbol that doesn't take any inputs, in fact. The number 0, for instance. The symbol for it is this, and the usage is also this. You see, now unlike addition, this symbol doesn't take any inputs. Addition requires 2 inputs, x and y, right? The 0 doesn't. It has no inputs. And so this reads simply as 0. It's still, out of no inputs, it still creates an object, the number 0. So it's seen as a term. And one can go on with this, and one can add and introduce one's own symbols as long as one describes what its intuitive meaning is. One can go ahead and do that. And all of these things, of course, will be very specific to what kind of mathematical thing you're working with, right? So all these things we've added here is now specific to the subject that you are studying with your mathematical language. There are, however, 2 further symbols on the logical side, which I should have introduced, and I forgot about it. But it's actually good I forgot about it, because I'm going to now explain them better once I already explained the symbol 0. So these 2 other symbols represent kind of constant statements. Like 0, you can think of the 0 as a constant value, right? They represent constant statements, which are the following. True, and the symbol for that is various. Different people use different symbols for that. One possible thing is just to write out true. And then its usage is simply this. Okay, so what is this? This is a statement. It has no input values. There is no alpha we need to create this statement. Just like 0 doesn't have any input variables, but it still produces an object out of it, the number 0. If our language talks about numbers, then we can use this symbol there. And here we have a statement just like all the other statements we've been getting here out of various alphas and betas, but this one does not need any alpha and beta. In fact, cannot have any alpha and beta. It simply produces a constant statement out of no initial statements to depend on. And the meaning of this is truth. So we basically have a symbol for truth. So it's of course it's a hypothetical thing, right? I mean, in practice, in real life, in ordinary language, you could have a true statement, but this will be a specific statement. It will not be just true, right? If I tell you, if we start speaking and suddenly in our conversation, my next sentence is true, full stop. That doesn't make sense, right? So it's something that we incorporate in mathematics, which is a bit abstract in the sense that we don't really talk in that language, in the ordinary language. And in some sense, this is a bit like the number 0, because I mean, the natural numbers 1, 2, 3, 4, 5, they arise by counting, right? And so if I've got 3 apples in front of me, I will start, okay, 1, 2, 3, I've counted till 3, therefore I have 3 apples. But now imagine I have no apples in front of me, then I don't count, I don't say anything, I don't pronounce anything, right? And that, the fact that there are no apples, we still have, even though I didn't do any counting, I still have a mathematical symbol for the quantity of no apples. And that symbol is the symbol 0. And it's important because when I didn't have anything to count, even though I didn't count anything, I still did something. I observed there were no apples. And so it's important to have a mathematical symbol for that observation. So in a similar way, the statement true does not have any specific meaning, but at the same time, it has a very, very specific meaning. It's a statement that's true. So whenever we use this statement, it will always be true. So the truth table for this statement is it's always true. It does not depend on anything else. It's always true. And then there is a similar one for false. We can also write this out like that. Some people sometimes use this symbol for true and this symbol for false. But in our videos, we're going to use just the full text, true and false. Actually, I'm changing my mind about this now. Since we've been using as many symbols as we could, why not represent these purely through symbols as well? But this T shouldn't be mixed up with the other T. We can use a different font if we're typing this up. So that's truth, and the other one is falsity or false. So we were saying here how we read this thing, right? And so we read this thing as true and we read the other as false. So once again, this is a statement that's not created out of any other statements. And this is a statement that is always false. Of course, the assumption that such statement exists can be considered as a strong assumption. And so one must be careful on that part. And similarly, this one, right? So the logic we will be developing, once we have the symbols, will be relying on the assumption that such a false statement actually exists, so we can have a symbol for it. But maybe somebody else would want to have another logic where this assumption is dropped. Okay, so we've got now all the ingredients we need for, you see it's quite a lot, we need for expressing various mathematical statements that will be constituting these individual lines in a bracket proof structure. And so let us, we already had a long discussion, 50 minutes, so let us try to finish soon, but we still want to have a look at a few examples of how all of this works, right? How we can combine these symbols to form more complex statements. And so combination of these symbols is very much similar to how you, for example, would combine addition to form long expressions, like, for instance, 2 plus 3 plus 5 plus 7, right? So what does this mean? This means that you first add 2 and 3, then you add 5 to that, then you add 7 to that. Now with addition, it doesn't really matter in which order you do this, but imagine if there was subtraction, then it would matter, right? So it would matter whether you subtract first 2 and 3 and then subtract that from 1, or whether you would first do this and then this, right? And so the brackets tell us what is done first, right? And so the structure of how the brackets work in terms of telling us what is done first in arithmetic is basically exactly the same as how the brackets will work to form logical statements and indicate, therefore, for us what is going to be done first. So, for instance, if I look at an example, let's say we say here for there exists x. So let me use a different color for this. There exists x such that for every y, x plus y equals y. So suppose we have something like that, right? Now, if I'm really honest about the bracketing here, I should include one more set of brackets, right? This one, namely. And then the brackets basically tell us what to do. So just like with the arithmetic, you start with the innermost bracket to first compute that and then build it up from there. In a similar way, we're basically saying here, okay, x plus y equals y, that's 1, x plus y equals y, that's something that we treat as alpha. In fact, we treat this as alpha xy because it involves two variables x and y in them, right? But we can just call it alpha. Okay, and now first this needs to be evaluated. This equality has a meaning of its own, right? So alpha holds that meaning. Alpha says x plus y equals y. And then we apply to that this construct of universal quantification, because that's what we encounter next when we zoom out from that bracket, right? So we are applying to it for all y alpha, right? So this part, this ingredient now becomes an instance of this thing here. So if the other one is alpha, this is that. And so now we recognize which symbol we're using here, right? Which line of our table we're using here. We're using this line there, right? Going back to the equality, so to form, of course, with the equality also, we read this as x plus y, and then that thing equals y. We usually skip brackets there, right? We usually write it like this, but if we are more precise, we should put it like this. And so that tells us that first we evaluate the sum. And so first we apply this line, right? First we make use of this symbol, the addition symbol. Then once that term is formed, so now we can think of as a variable z, then we have equality. That's what comes next. And so then we use this line, right? And so in that sense, this breaks down further into actually into two things, because the thing that was used just before was x plus y and y. And so we could think of x plus y as z, and this one we can think of y. And so these are combined together under equality. So alpha says z equals y, so maybe I should write here equality symbol, because that's the operation we use to combine that. And here maybe I should write just for all y, so that my this tree I'm displaying here kind of holds the information of what that input here is. That input is whatever is read through the thing that comes after, right? So I'm going to be using equality to combine z and y, and z itself is made out of two ingredients, x and y. So that corresponds to breaking this down into x and y. And then going back to the top there, once we form this, then there is just one more step remaining. Then we say there exists x such that, right? And so we're now operating on this with the existential quantifier, but with variable x instead of y, right? So you see this kind of picture gives you a breakdown of what happens first according to the bracketing and what happens after, right? And it's very similar how it works in arithmetic. When the innermost brackets group things together, first that has to be evaluated as one thing, and then we move out, step out of the bracket slowly, and then eventually we evaluate the whole expression. Now, what about the logical? So, I mean, there is a certain effect on the logical meaning that this now has, because each of these lines here in this table had their own basic fundamental kind of building block meaning, but now the overall statement has its own logical meaning that's kind of composed of those basic meanings. And so let's try to read what the meaning of this thing is. Unlike arithmetic, perhaps, when we try to interpret the logical meaning of this, instead of working from bottom up, as we have done now, we actually want to work from top to bottom. So we want to look at, first we want to look at the outermost statement, which is that exists x. So now we're told that certain x must exist, and this x must have certain property. And so let's see what kind of property the x must have. Okay, now the property is that for every y, something should hold. And so now let's see what that something should be. Right? So we now are told that there is a certain x such that no matter what y we will pick, we will have that x plus y equals y. And by interpreting this step by step like this, by going top to bottom on this tree, we eventually start to see the logical meaning of this, and we say, oh, wait a second, such x does exist indeed. That's the number 0, right? Number 0 has that property that whatever number y you pick, 0 plus y will equal to y. So such x does really exist. The x that has this property does exist, right? Okay, so you see, that's how these more basic building blocks can be used to create sentences with combined meaning that will have its own independent logical meaning, and it will be meaningful in the given context. I just want to conclude here by showing you an example where we will see that it matters the order in which we read these things. So imagine now, instead of the order in which we did, which is the right order according to the brackets, we swapped the order around and we said, for every y, whatever number you pick, there is an x. So I swap around now the order among these two. Whatever number y you pick, you can always find an x such that y plus x equals y. Well, that's true as well, right? Whatever number y we pick, we can find such x. This x is 0. But instead of x plus y equals y, what if I had for every y there exists x such that y plus x equals 0. This is still fine because we're saying for every y there needs to exist x such that y plus x is 0, and that actually will be true because we can pick x to be minus y, so such x really exists for every y. But now if I swap the order around, now we will be saying that there is a specific x such that this whole thing is true for that x. And what does that whole thing say? It tells me that every single y that we add to this specific x gives me a value of 0. And that's of course impossible. You cannot add different values of y to the same x and always get 0, right? Because first we have to specify x, and then we have to consider arbitrary y's, and once we consider arbitrary y's, we can't change the x anymore, right? Because that x needs to exist that has this feature, where once we start engaging with this feature, the x becomes now fixed object. Okay, so what we did in this video was to kind of go through the basic building blocks of forming sentences in bracket proofs. And I want to emphasize one more time that these are just the basic building blocks. We can create complex logical sentences using these building blocks. And the way we create them is very similar to how in arithmetic we combine various different operations and other symbols to create meaningful sentences. And so then the bracketing there, these brackets there, the ones we've shown here, shows us the order in which things have to be done. And then another thing to keep in mind is when we eventually build up a statement, which usually, so the bracketing will kind of tell us how things are grouped, and the bracketing structure kind of gives this tree bottom up. But when we want to understand the logical meaning of this statement, we want to read it bottom to top, top to bottom rather. Because when I can't really interpret the logical meaning of this on its own before I know that there must be a specific x for such that for every y something will hold. So this is where we have a slight difference to how we do things in arithmetic. I mean, in a way, we also encounter this phenomenon in arithmetic. Imagine you have x plus y less or equal to z plus t, right? And so when you try to read the meaning of this, the logical meaning of this, you would first pay attention to less or equal before you pay attention to plus. So for you, this is, okay, some number is less than the other number, and now after that you look into what these actual numbers are. So that's a similar process that we've done there, where we first identified this as existence of some x such that for every y something will hold, and then only after we looked at exactly what that thing should hold for every y and a given x. Okay, so that's it for this video, and we will in the next videos what we're going to discuss is how can we get sentences as logical conclusions, can we get these lines in bracket proofs as logical conclusions of previous lines by looking into the structure of the lines in terms of these symbols. And we will see there that for each line what will really matter is what lies at the top of the structure, what is the outermost logical operation we're performing. That will really be the thing we're going to be looking at to see how we can get a specific line as a conclusion from the previous lines. And so this breaking down of a statement into this hierarchy that we've shown here will kind of be implicit in the way proofs will be structured through statements composed of these logical symbols. That's it for this video.